All right. Today I want to talk about beyond the grids, and the alternative title would be where do galaxies get their spin from? And they didn't get it from their mama. And in order to do that, I'm going to talk about angular momentum, tracer particles, and data analysis. And the reason why I talked about beyond the grid is not any Tron reference. I'm sorry, Matt. But because in order to achieve this project, I had to extend quite a lot the way YT handles particles and grids and the way they interact one with another. Um, but I'm going to discuss all of that in this presentation. So first, very busy plots, and just to give some feedback. The points of the research I'm going to present is to understand the origin of galactic disks. So at a high redshift, so early in the history of the universe, these disks are we see them all over the place in simulations, but also in observations. However, we don't really understand theoretically how they form. And so in order to understand how a disk form, you have to understand where it got its rotation from. And in order to understand the rotation, you have to understand where the angular momentum is coming from. And one very clear feature from simulations, as you can see on the bottom, um, is that gas that is being accreted on galaxies at the center of all of these plots with different codes. They come from particular directions along what we call filaments. And so today what I'm going to study is the accretion of angular momentum along this filamentary structure. And I'm using the code Ramses for those of us who are interested in that kind of stuff. And in particular, as I mentioned, these flows along which gas is being accreted, if you look from the right to the left, so from quite large scale to very much smaller scale, you see that they're quite filamentary, but also if you look at the temperature, they're actually cool. So for those of us who are not doing astrophysics, for me, cool means below 10 to the 5 kelvins, doesn't mean below 0 degrees Celsius. So what I call cool is not really cool for anybody else, apart from people doing the same stuff as me. But it's quite striking that the gas is being accreted in this cold phase. And so in order to understand, well, to spot this filamentary accretion, one way to do that is to be able to tell whether the gas is being accreted cold or hot. All right. Okay, so the plan for today is I want to study the angular momentum kinematics in these flows. So with YT, that's really easy because I have access to the gas position, the gas velocity, and the gas mass. So I can compute the angular momentum, and I can study that as a function of all sort of stuff. For example, the radius to the distance to the galaxy. The second thing is that I want to study accretion flows for that. So for that, I have to know which gas has been accreted and not gas that is being accreted, but that has been accreted. So I need the entire history. And Ramses is grid code, which means that I know gas quantities in cells, but I don't know where it comes from and I don't know where it's going. So for this, I need like the Lagrangian history, the Lagrangian trajectories that we already had a presentation like 2 days ago. So this is not in Ramses nor in YT. Then I need to know whether it's being cold or hot accreted so that I can distinguish different modes of accretion. So for this, I need to have the temperature along the trajectory. I'll come back to that point later. Um, Fourth point is that I need not only well, once I have the kinematics, I have to understand why angular momentum is changing. And well, you know from physics that angular momentum change whenever there are torques. And I can compute quite easily the torques if I can compute the forces and the radius using this simple formula. So in my case here, I'm going to focus only on pressure and gravitational torques, which depend on the gradient of the pressure and the gradient of the potential. The gradient of the potential is already provided by the simulation, but the gradient of the pressure is a bit tricky, just because it's not computed directly. All right, so let me first start with my first point. So I want to study the angular momentum kinetics. There's nothing to do because I know how to do it. So now the first thing to achieve is to reconstruct the Lagrangian trajectories. So for this, Very briefly, Ramsys is an AMR code, which means that I have density on a grid. And what I want is to know where, for example, this red blob of gas comes from. And I just drew using paints. But in practice, it's not really enough to draw using paints. You have to have like a robust method for that. And so for this, the question is how to reconstruct the Lagrangian history in a Eurian simulation. And the answer, of course, is tracer particles. So how do we do it? There are mostly two ways it's been implemented. Either using velocity, so you interpolate the velocity at the location of the tracer, and it gives you, for example, this is the distribution of tracer particles in one of my simulation using this velocity approach. The other possibility is to use Monte Carlo base. So instead of trying to reproduce the velocity, we try to reproduce the fluxes, and it gives this image here. So let me just compare the two of them so that we know um, which of the two is best. Ooh, ooh. Okay, so if I take the difference of the density minus the density reproduced by the tracer particle, I should get 0, meaning that the tracer are exactly distributed the same way as the gas. If I do that with velocity, you see there's a lot of residuals, and with the other implementation, the Monte Carlo, there's almost none. So I'm going to use this one. And if I just want to very quickly give an answer of which one you should use, well, you should use Monte Carlo based tracers. So I've been using them to try to reconstruct the Lagrangian history. Okay, so far so good. So if I just go back to the to-do list I had, so I said that I know how to compute the angular momentum kinematics. I know I also have a recipe to compute the Lagrangian trajectories. So the third step is to be able to extract the temperature along the Lagrangian trajectories. Okay, so how do you do that? Well, in practice, what I have is I have some greedy data, for example, density, temperature, and then I have tracer particles, which are particle data. And well, we know from in YT how to project, for example, particle data onto grid data using CIC or nearest interpolation. That's quite easy to do in YT. You can do it in like 8 lines if you are black fanatic. Otherwise, you can do it in much less. But essentially, you use this method, deposited particle fields. Here, I deposit my tracer, the particle mass of my tracers onto the grids, and then I have some data living on the grids, which is tracer CIC mass, and I can make a plot and get this. The issue is that what I have is I have tracer particles, and I want the data that lives on the grid. In practice, what I want is I have the particle, and I want to know the value of the grids at the location of the particles. So how do we do that? Well, a couple of years ago, the way I started doing it is using this ds.r approach. So you can give it a position, and then you can compute the density, for example, at this position. And if you repeat the process for all your particle data, you eventually get, for example, in this case, the density. The issue is that, for example, in this case, if I run it, it takes about 3 seconds for 1,000 particles. And in my simulation, I have 100 millions. So that's not really practical. So the way this has been solved, and it's now in YT, is implementing the same approach as CIC, except it's the other way around. So it's a mesh deposition. You sample the mesh at the location of each of your particles. And the way it's implemented is really similar to doing a CIC deposition, except it's the other way around. So I do add mesh sampling particle fields, and I want to sample the gas density wherever I have tracers, and then I have a new particle field, which is cell gas density. And this time, instead of taking 3 seconds for 1,000 particles, it took 1 second for a million particles. So that's much better. And then once you have that, you can make particle projection plots using the tracer and the value of the gas at the location of your particles. Okay, that's cool. There's also a small trick if you call, so that's working for any greedy data, so octree or grid-based. If
You
you
have
call
about
cell,
5 minutes left, by the
oh
way.
no, okay, okay, I'm going to jump, cool. Right, so we know how to compute the temperature. The torques actually are really easy to compute once you know the forces. So I'm going to say that's easy. The last bit that is missing is how to compute the pressure of the gradient pressure. We have the pressure, but not the gradients. Why is it an issue is because I'm using OCT datasets, and OCT datasets are 2 by 2 by 2 cube, which means that you have only one neighbor for each cell. You have only one neighbor. If you want to compute the gradient, you need 3 points. You need the next cell, the previous cell, and the current cell. So how do we do it? Well, the way we do it in YT is using ghost zones. So here I represent them in green. And essentially what we do is we compute the value of the field around these virtual cells, and then it gives 4 cells Y, which means that you can compute the gradient of the pressure now. Yep. And then you can take like these values and put them back in your formula, that you've got your gradients. Cool. Okay. So it means that we've got everything. So I don't have a lot of time, so I'm going to go quite quickly. No, I can compute the kinematics using my tracer particles. So I use, so here on the x-axis, I represent the distance to the galaxy. On the y-axis, the amount of angular momentum. And these two trajectories are for the cold and the hot gas that I define using background history and the temperature. And the direction of accretion is from right to left. So the gas is falling. And what you see is that on large scales, you've got a high value. And on small scales, you've got a value that is much smaller. So you decrease your angular momentum by a factor of 5. And the question is why? So for that, you need to go and study the dynamics. Okay. And if you study the dynamics, the first thing you can do, well, you compute pressure gradients at the location of your particles, and you get a profile like this. So here it's the distance to the galaxy, and y-axis the for radial acceleration. So it's more or less the torque, and you see that well, you've got quite a high torque. Then you can compare that to the gravitational torques, and you get the fact that in the region where you're accreting, your pressure torques are higher than any gravitational torques. Okay, that's cool. Okay, except that here I only talked locally. So I was looking at the magnitude of the auto-radial acceleration. So if you average over all the tracers being accreted in one shell, here it's still the x-axis is still the distance to the galaxy, except this time I've averaged over the entire shell instead of just summing the vectors. And then I get something that is quite different. Let me just plot the ratio of the gravitational torques to the pressure torques. And so I mentioned before that the pressure torques are dominating locally, but when you average over a shell, you get the exact opposite answer, which means that at least in the cold phase, your dynamics is dominated by gravitational torques. Um, how long do I have?
You have about 2 more minutes.
Okay, so that's just repeating what I just said. So essentially, you've got something that is dominating locally, but then when you average globally, it's not dominating anymore. So what is happening? What you can do, for example, because I know I have access to all cells, but one cell goes to the trick, that you can do the sum of the torques divided by the sum of the magnitude of the torques. You've got a value that is equal to 1, which means that all the vectors are aligned one with each other, and all the 27 cells are at once. If I
Hey,
get some,
Corentin,
Yeah, your
you're
audio is getting a little distorted. Do you mind turning off your video for a minute?
okay,
Thank you.
better?
A little bit, yeah.
Okay. So essentially, you've got a value of 1, it means that's very coherent, and if you've got a value of 0, it means you're not coherent. And what you see is that in the pressure, you have quite a small value, which means that the vectors are just aligned randomly. And when you average over an entire shell, you get something that is you get opposite contribution. And I think I'm jump to yeah. Okay, so I presented like the kinematics, showed that the angular momentum is transported. I didn't have enough time. Then going to the dynamics, the pressure dominates locally the dynamics, but globally it's dominated by gravity. The reason for that is because torques have a special variations on very small scales for pressure, and it's not the case for gravity. And in order to do that, there's many cool features that have been brought together. So the trend transfer in Ramsys, the mesh sampling in YT, the ghost zones for octrees, which enable gradient computation. But also, they also enable vertex center, which means that volume rendering. And I'm going to stop on a volume rendering. Some questions. Yeah.
Ooh, thank you. I'm clapping for everybody. I think we have time for maybe one question, and then I encourage everybody to ask questions in Slack. I also just want to make a comment about your talk is that you have incredible viz in the background of all your slides, including this super cool volume rendering. Thank you so much for showing us all of this, Corentin. It was really, really beautiful. I can't wait to look through your slides later. So do we have any questions? It looks like Britton has his hand raised. So Britton, I think you can go first.
Thanks. Corentin, that was great. I really liked it. I just wanted to ask, do you think that the fact that the cold, now correct me if I just misunderstood, but it seems you say that cold gas is dominated by gravitational torques. Is that because the cold gas is coming in via filaments?
Yeah. What's the question?
Is the cold gas angular momentum coming from gravitational torques because the cold gas is coming in via filaments?
So essentially, both the cold and the hot gas have their local dynamics dominated by pressure torques, which means that the pressure is just like controlling the local changes. But then if you average over a shell in the cold gas, because the cold gas is a bit more homogeneous and it's a bit the pressure torques, they average out for the cold gas. And then the only contribution that is left is the pressure torques, which means that as the gas is falling onto the galaxy, it's interacting with the gravitational potential of the galaxy, and it's losing angular momentum, and it's actually giving some angular momentum to the galaxy. Does it answer your question?
Yes, thank you. That's great.
And if you compare that to previous studies, people have been finding either that pressure torques are dominating by 5 order of magnitudes or the other way around. And usually it's because they only look at local dynamics and not on the global scales. And you get something really different.
Okay, great. Thank you, Britton. I think we'll take one more question from Mike Meehan, and then I encourage the rest of you to ask your questions in Slack. So Mike?
Thanks. Just real quickly, because I know we're running short on time. Did you check, or like, how do you deal with the extending the ghost zones for boundaries that aren't, that have different levels of AMR?
Yep. So the way it's done right now is that I interpolate, I do a 0 order interpolation, which means that if the next cell doesn't exist because the AMR is coarser, then I just interpolate. I assume that a cell that doesn't exist has just the same value as its parents. And in the case of the other situation where the next cell is also refined, I take the average of this cell, of the 8 cells. Does it answer the question?
Yep, that makes sense.
Yeah.
Thanks.
But so you can also do some linear interpolation, but it's not being implemented.
Okay. Thank you.
Okay, thank you, Mike. And thank you, Corentin, again for an incredible talk. That was really, really wonderful.